So the response spectra is basically the herein already the time history and the response spectra are interlinked. Uh, we have carried out the time history analysis in the ETABS, and what we learn is that for a specific time history, we are applying on the structures and we are noting the response of the structure at different time instants. And the advantage of that time history is that for a specific time history, we can get the peak response of the structure, and we can also see the variation in the response of the structure. And you have seen that at any time instant, not necessarily that when the time history response is at peak, but at any time instant, the building can basically deform and show the peak response. So now the point is that what is the linkage of the response spectra with time history, because time history is also a time dependent analysis, and we can apply on the building a force which is varying with time, that is a time history. Then how to apply the response on the building, and what is the response spectra, and how to obtain the response spectra, how to design the response spectra, and how we can develop the response spectra, and what is the difference. Of course, people are following both of these analyses. Mm, Actually, either you follow the time history analysis or sometimes you can follow the response spectra analysis. So it depends that how you are applying the load and how you can get the results. So mainly why we need the response spectrum, the point is that in order to perform the seismic analysis and design of a structure to be built at a particular location, the actual time history record is required. Of course, the time history analysis actual is required, because normally the time history analysis we are getting for the certain sites where the accelerometers are attached. Now the point is that to perform the seismic analysis, the actual time history analysis is required. However, it is not possible to have such records at each and every location, because it is very difficult, and only in a country there are only few locations where we are getting the time history analysis results, time history data. And if you want to make some building which is 100 km away and you say, okay, we can follow the same time history data. So sometime it is, sometime it can be definitely not exact what we follow from the time history record. In addition, the seismic analysis of the structure cannot be carried out simply based on the peak value of the ground acceleration, as the response of the structure depends upon the frequency content of the ground motion and its own dynamic property. In addition, if you say that you know that the time history is giving us the peak acceleration of the ground and also the variations at different points with respect to the time. However, we know that the structure response cannot be only dependent on that single parameter, but in addition, the frequency of the ground motion, the time period of the buildings, and its own dynamic properties actually also can play a role. So why not we should develop an alternate graph which is depending upon the time period of the building. So to overcome the above difficulties, actually the earthquake response spectrum is the most popular tool and in seismic analysis of the structure. So basically to overcome the above difficulties, we will be working with the earthquake response spectra, and this is the most popular tool. Actually, the response spectrum is also then applied on the building, and it is linked with the time history also. And you will see today that how the response spectrum is linked with the time history. The response spectrum is basically an important tool, and it represents the maximum response of a damped single degree of freedom system to a particular input motion at different natural time period. This is mainly the response spectrum definition, that an important tool that is used in the seismic analysis and design of structures, and it describes the maximum response of damped single degree of freedom system to a particular input motion at different natural periods. So at different time periods of the building, we get the peak response. First, we have to get the peak response from the time history curves for the different time periods of the building. So different equipments are basically accelerometer. That is recorded, of course, for the different time period. Let's say for time period 0.1 second, 0.5 second, 1 second. We can note the response of a system, spring mass system, and note down the time history analysis for any particular point for the different time periods of the system. And for those different time periods, we can now note the peak response. We can pick the peak response from each time history, and we have the peak response and a time period, that for this time period of the system, this was the peak response. This time period of the system, this was the peak response. And then we can plot separately the peak response versus the time period. So that is the response spectrum. It describes the maximum response of the damped single degrees of freedom system to a particular input motion at different natural periods. Response spectrum method of analysis is advantage as it considers the frequency effects and provides a single suitable horizontal force for the design of structure. So normally it is giving us the single force. It is advantage because it considers the frequency effect. It is also considering the frequency effects and provide a single horizontal force for the design of structure, and that is a peak force that is basically obtained from the response spectrum. Now the point is that what is the difference between the response spectrum analysis and time history analysis? So basically the two basic methods are widely used for the dynamic seismic analysis, and these are the two methods, and one method we have already studied in the response of in the previous chapters, where we have studied the time dependent response of the harmonic motion, where the force was the time dependent. So that was the time history method. Now the response spectrum is the another method. You can apply any one or both to the building. You can compare the results. Here in this slide you can see the two points and two pictures also. One is a response spectrum analysis, and other is a time history analysis. So the first one is response spectrum analysis. The response spectrum analysis allows estimation of the maximum modal response of a singly supported structural system singly supported structural system of a or a multiple supported system where all the supports receive the same excitation. So you can see that either a singly supported system where it is a single response, or the multi-supported structural system, all the supports receive the same excitation. So in this case, in the response spectrum method, we can find out the maximum modal response of a structure where we are applying a peak load to the structure. Whereas in the time history method of analysis, This permits the simultaneous application of the different excitations at each support point or uncoupled model of the system of interest. So time history analysis is basically applying the different loadings at a different instant. The time history is basically varying, and we have to develop the certain functions of the time history which is varying with the time. Whereas we apply the peak response in the uh, response spectrum analysis. The time history data is obtained from the accelerogram and the most direct descriptions of an earthquake motion in time domain is provided by accelerogram that are recorded by instruments called strong motion accelerographs. So accelerographs, basically strong motion accelerographs are attached with the different critical sites like in Pakistan at the Bela Dam. It is also attached and the meteorological centers and other critical defense locations. These are attached so that even in high class data centers, I mean these things are attached, and we can record the seismic motion with respect to the time, and the accelegraph record the three orthogonal components of the ground acceleration at a certain location. Basically, the three components are can be recorded from the accelerogram. These are included in the acceleration, the velocity, and the mm, displacement at a certain location as a function of the time. And normally, the peak ground acceleration, duration, and frequency content of earthquake can be obtained from an accelerogram. So peak ground acceleration can also be obtained, the duration and the frequency content of the earthquake can also be obtained. What was the duration? Because there is a time on the x-axis and the peak response and the response on the y-axis. An accelerogram can also be integrated to obtain the time variation of the ground velocity and ground displacement. Normally, the acceleration is recorded from the accelerogram, and you can basically it can be accelerated, integrated back to obtain the time variations of the ground velocity and the ground displacement. Not directly, but indirect methods of conversions are available even in the computer aided simulations, where you can convert the accelerations and into the velocity and then velocity into the displacement. Herein you can see some time history data for the different earthquakes like El Centro at the top left, and on the scale is also shown here somewhere, and on the right side 0, 0.5 or 1. This is in the multiple of the G, where G is the 9.81 meter per square second. So there are the earthquakes in 1940 of the El Centro. The data of this earthquake is completely available. Even in your book, the tables are available, these time history tables. Parkfield, similarly, the San Francisco in 1957, and it's in the 1971, and then the earthquake from the Helena in 1935, 1994 Northridge, uh, Parkling, and other earthquakes. You can see the Chile earthquake in 1985 and the Mexico City earthquake also. So all these the data is available, and time history for these can be obtained. Even for the Pakistan earthquake of 2005, the time history is available. So analytical solution directly is not possible for earthquake excitation. You have seen that the data is highly haphazard and irregular. Therefore, the numerical methods are basically employed and to find out the other quantities like the velocity and displacement. Here you can see the graph of the earthquake excitation and mm, this one. And the numerical methods are basically available to compute the velocity and the displacement. So different numerical methods are the central difference method, average acceleration method, Newmark's method. You can see in one of the chapters in the dynamic analysis book. However, we are not going into the detail of computation of these parameters, but of course, the persons who are mathematicians are basically involved in converting all this data, and there are the different equations are available. We can actually obtain that. There are many methods. You can just visit that chapter, and overall you can see that. If we have some time, then we will try. But nowadays, because of some new computer aided softwares, it is possible to make a routine and develop a method so that we can convert the acceleration obtained from the time history data to the velocity and the displacement. So here in this picture you can see the three basically graphs. First one is acceleration for the same earthquake record, and the maximum acceleration is at 2.04 second 0.318 g in terms of g, where g is 9.8 meter per square second. Now you convert that, when we convert that and integrate it to the velocity, then the maximum velocity you can see is obtained at about minus 380 minus 380, and it is not obtained at the same time. It is obtained at 1.53 seconds, because the time is also, when you are doing the integration, also the time limits is also implied. And third one is the displacement, that is obtained again from the integration of that velocity, and you can see that the maximum is minus 212 or like that, and it is obtained at the 2.62 seconds. So this is basically the conversion of the time history data from the obtained data, which was the acceleration, and converted into the velocity and displacement. And you can see the difference of the curves, the acceleration graph and then the velocity graph and the displacement graph. Now you can pick the peak value from these, that what was the peak value, and each data which is obtained is for specific time period. It is for the specific time period. One complete set is for specific time period. Time instant is something different, that at this time the response was at peak, and time period is of the system. The time to complete one vibration is a time period, and this time which is we are noting is basically the time at which the peak response occurs. Now it can be shown here another graph where the north-south components, these actually are also given in your book. For a specific El Centro earthquake, they say that this was the peak acceleration was 0.319 g, and the peak velocity was u dot g is 13.0 of the ground was 13.04 inch per second, and the displacement obtained was 8.40 inch. Now these peak values can be picked from the graph, and you can plot the response spectra. For example, here you can see now that for time period 0.5 second and damping ratio 2%, the deformation response obtained for any specific system is 2.67 inch. When time period was 0.5 second, when time period was 1 second, it was 5.9. When time period was 2 second, it was 7.47. All are deformation of response, and then you can plot now the on the x-axis the time period that okay at 0.5 second you put some values at 1 second, and similarly in between this you can have the many values between these main time periods actually through the computations, and this is the response spectra. This is the deformation response spectra. What it is showing, you have to obtain the data from the 3 time histories and you get 3 points. So as many number of time histories are available, more will be the data available for the response spectra. Here you can further read it in detail that for a given earthquake excitation, calculate the U maximum from the single degree of freedom response with a certain damping ratio and within the range of the natural periods or frequencies. On the right hand side again you can see the ground acceleration record, and on the bottom you can see the displacement response, deformations or displacement, and for the different time periods you can obtain the deformation response for the different time periods from the time history data. And now you pick the peak value from each curve and plot on the bottom figure on the right hand side is basically the peak value is picked up, then it is plotted. Here the peak value of this one, which is for the time period 0.5 second. This is plotted at this point. The peak value from this one is plotted at this point. The peak value from this one is plotted at this point. Now this is the response spectra. We are now we obtain the response spectrum, and the U maximum for each frequency will be found from the computed history at this frequency. Basically for each frequency the U max is obtained, and a plot of the U max versus the natural time period is constructed representing the deformation or displacement response spectra. Response spectra is not only for the one quantity. You can have the response spectra for acceleration, you can have the response spectra for the velocity, and you can have the response spectra for the displacement. In the last lecture I was telling you something that RD, the displacement response factor for displacement, and RA and RV in the force vibration. And then when we plot all this, it was you was able to plot on a single graph also. So there was basically the functions which were obtained like in the last lecture, that you was getting some function like that, displacement acceleration response spectra, and similarly the similar kind of a function by we can be obtained for the velocity, and finally on a special log plot you was able to plot it in a single way on a single graph which was called as the DVA spectra, displacement, velocity, and acceleration spectra. So similarly, the response spectra is linked with that. It is also linked with that, and we can obtain the peak response, and we can also plot the response, DVA response, and later on you will see, and I will show you some graph that from the single graph you can obtain the three quantities for one specific time period. You can obtain the peak displacement, peak acceleration, and peak velocity. From this figure, one can directly read the maximum relative displacement of any structure of natural period and a particular value of the zeta as damping. So you have the zeta value. Damping also is very important because change of damping change the response. We obtain the, by picking the peak values, we can obtain the response of the system. Herein further, a central ground motion time history for the different time period is plotted, is seen. Time period 0.5, 1, 2, 2, 2 second, 2 second time period, and damping is changed. What you see that when the damping was lesser, the response was 9.91 inch. When the damping was 0.02 and the time period was 0.5 second, so you can compare that the time period was 2 and the damping 0.02 in the last picture and the damping is high. So with the change in the damping, of course, the response also changes. Higher is the damping ratio, the lesser is the response value. And similarly, with the change in time period also, you can see that the response is also changing. And this graph is clearly explaining about the effect of the time period and the damping ratio on the response of the system. This was the deformation response of the single degree of freedom system. This is the acceleration response. You can see that at time period 0.5 second, the acceleration is 1.09 g. When the time period increased, the response reduces. And when the time period further increase, and of course you can also see that the behavior, the overall, the time, of course, when the time is increasing, the time to complete one vibration, of course, the curve will also change. So the damping ratio is constant in this case, but the time period is varying. So by increasing the time period, the peak response also changes, reduces. And similarly for the damping ratio. And finally, for any damping ratio and for different time period, one curve is for one damping ratio. We need the multiple curves because one curve is not sufficient. One response spectrum curve is for the one specific damping ratio. For the varying the time period, you can obtain the peak response, and you can see that one specific curve is plotted for the, like for this curve that you can see in the right hand side, is basically for the damping ratio 2%, 2%, time period is 0.512. So time period is on the x-axis, and you can obtain the one curve. This is for the one damping value of 2%, and the peak response values are also available. The point is that this response spectra, practically, if you want to interpolate it, it's very difficult, and between two time periods, normally the obtained response spectra, of course, it is irregular. So normally the design spectra is built from the response spectra. You can make a elastic design spectra that will be explained in later on. This is the response for one specific damping, and for 3 time periods, the response, you can see the difference of response. The first one is the displacement response. Second one is the velocity response, inch per second. Third one is acceleration response. You can see that these are interlinked actually, and actually we can make some relationship so that these 3 quantities can be interlinked, and if the one quantity is computed, the other can also be determined. So the relationship that is available is we know that the A over omega n is equal to the velocity, and velocity is also equal to the omega n into d, or Tn over 2 pi into acceleration is equal to velocity, and at the same time velocity is equal to 2 pi over t into the displacement. Here d represents the capital D represents the displacement response, capital V. This is a pseudo relationship. This is a pseudo relationship basically between the dV and A. Because V A over omega n is equal to V, so it means that omega n is equal to the basically the omega, the units based and dimension analysis based conversion have been made, and you can see that the velocity and displacement, velocity is equal to 2 pi over t into d, because d unit is meter, time period unit is in second, so v is equal to d over t, 2 pi over t, because 2 pi over t is omega, so v is equal to omega n into d. From that you can make the other relation. Why? Because v is also equal to acceleration unit is equal to meter per square second, and it means that if you divide the acceleration by omega and reduce 1 second, so a over omega n, because omega is in radian per second, and it will be obtained as the meter per second. So in this way this relationship is built. It is further explained here. It means that the velocity is equal to omega n into d, where acceleration is equal to omega n into v, and similarly the velocity can be obtained from the 2 pi over Tn into d, and acceleration can also be obtained as equal to the from the right hand relationship. If you see, acceleration will be 2 pi v over Tn. So in this way we can obtain the relationship and the peak response of the we can interchange it and obtain the value of the displacement velocity. If one is available, the other can be available. Basically the function d is the displacement response, sd
सर
is a
एक्सक्यूज मी
function. Yes.
सर, ये एक पॉइंट थोड़ी कंफ्यूजन है और समझा दें सर। ये जो टाइम पीरियड फॉर एग्जांपल इंक्रीज हो रहा है, तो वहां पे हमारे पास जो ग्राउंड एक्सेलरेशन है वो कम हो रहे हैं, लेकिन डैम्पिंग इंक्रीज हो रही है। सर ये थोड़े पॉइंट एक्सप्लेन कर दें आप।
नहीं, डैम्पिंग जो है वो तो एक गिवन है ना, वो स्ट्रक्चर की प्रॉपर्टी है। यहाँ पे आप बता रहे हैं डैम्पिंग कैसे इंक्रीज हो रही इस
सर ये जो
ग्राफ
टू
में?
जी जी सर,
डैम्पिंग यहाँ कांस्टेंट है।
सर डिफॉर्मेशन की बात कर रहा हूँ।
बात कर रहे हैं मेरे ख्याल, वो बढ़ रही है
डिफॉर्मेशन
ना?
की बात कर रहा हूँ। जी जी सर।
हाँ जी।
जी सर, ये डिफॉर्मेशन की बात कर रहा हूँ। वहां पे ग्राउंड एक्सेलरेशन कम हो रहा है, यहाँ पे डिफॉर्मेशन ज्यादा हो रही है। सर यहाँ पे थोड़ी कंफ्यूजन है।
इसमें आपके पास जो आपके जब इंटीग्रेट करते हैं ना, आप देखें कि एक्सेलरेशन जो है दैट इज इंटरलिंक्ड विद दैट। यहाँ पे आप देख रहे हैं ना एक्सेलरेशन वाला, ये डेफॉर्मेशन वाला था ना, ये एक्सेलरेशन वाला था, ठीक है ना।
यस सर, यही है
तो
बिल्कुल।
आपका जो एक्सेलरेशन है दैट इज इन मीटर पर स्क्वायर सेकंड, इसकी अपनी एक यूनिट है, फंक्शन ऑफ द जी। यानी कि आपके पास एक स्ट्रक्चर है, एक्सेलरेशन है कि हाउ मच इज द रेट ऑफ चेंज ऑफ वेलोसिटी विद रिस्पेक्ट टू द टाइम, ठीक है ना। वेयर एज डेफॉर्मेशन जो है दैट इज द मैक्सिमम डेफॉर्मेशन जो आप ऑब्टेन कर रहे हैं, यानी कि एक्सेलरेशन यहाँ पे ऑल दो कम हुआ है एंड नॉट नेसेसरी कि इसी पॉइंट पे डेफॉर्मेशन पीक आए। जो बिल्डिंग का रिस्पॉन्स है ना, अब वो अगर आप देखें तो दैट इज ओनली द रिस्पॉन्स ऑफ इन मीटर्स, वो आपके आंसर इन इंचेस में या मीटर्स में है, तो वो इंक्रीज होगा क्योंकि इनका जो आप रिलेशनशिप भी यहाँ पर देख रहे हैं जो आपस में जो है ना, यू कैन सी कि ये इट्स नॉट लिंक्ड कि डायरेक्टली ये ऐसे नहीं लिंक कर रहा होता कि एक्सेलरेशन बढ़ा है तो वेलोसिटी भी इंक्रीज होगी और डिफॉर्मेशन भी इंक्रीज होगा। ये बिल्डिंग का रिस्पॉन्स है, तो वो डिपेंड कर रहा है। जब आपका टाइम पीरियड देखें ना आपका इंक्रीज हो रहा है तो आपके पास इसका मतलब है कि टाइम टू कंप्लीट आपका वन वाइब्रेशन भी बढ़ रहा है। इसका मतलब है कि वो जो स्वे आपके पास हो रही है लेटरल डेफॉर्मेशन वो ज़्यादा होती जा रही है जैसे जैसे आपका टाइम पीरियड बढ़ा है ना एक बिल्डिंग का, बिल्डिंग इज टाइम, उसका मतलब है कि उसकी डेफॉर्मेशन वो सेम अगर बिल्डिंग की डैम्पिंग है, बिल्डिंग की प्रॉपर्टीज बाकी सेम है और टाइम बढ़ रहा है तो डिफॉर्मेशन एट द सेम टाइम आप अगर देखें acceleration will reduce। तो जैसे जैसे वो टाइम पीरियड आप इंक्रीज करते जाते हैं एक्सेलरेशन कम होता जाएगा और जो डिस्प्लेसमेंट है वो इंक्रीज होता जाएगा। तो यहाँ से भी आप देख सकते हैं ये एक स्पेसिफिक यानी कि डैम्पिंग रेशो के लिए है, अगर डैम्पिंग रेशो कांस्टेंट होगी। लेकिन डैम्पिंग अगर आप अब किसका फंक्शन बन गया है, आपका जो डिस्प्लेसमेंट है वो टाइम और डैम्पिंग का फंक्शन बन गया है। एंड इफ यू डिवाइड द वेलोसिटी रिस्पांस बाय ओमेगा, क्योंकि ओमेगा इज अ फंक्शन ऑफ द टाइम एंड द zeta, and if you divide this function by the uh, omega, then you can see the time। ये सारे बेसिकली टाइम और उसके फंक्शंस है ना। लेकिन इसको आपने जब एस वी और ओमेगा करेंगे तो यू विल गेट द वेलोसिटी रिस्पांस एंड व्हेन यू डिवाइड बाय ओमेगा स्क्वायर तो फिर आपका ये तीनों आपस में इक्वल हो जाएंगे। और एस डी यू कैन राइट इट एज टी इंटू ओमेगा, टी इंटू एस वी डिवाइडेड बाय 2 पाई, क्योंकि ओमेगा इज 2 पाई ओवर टी होता है पुटिंग द वैल्यू ऑफ ओमेगा, और इसी तरह ओमेगा स्क्वायर विल बी 4 पाई ओवर टी स्क्वायर। So this is basically interrelated in this way, and that is also seen here. In this way, we can interrelate the displacement response. SD is basically SV over omega, and that is also equal to acceleration response over omega square. So this relationship basically is interlinked into three quantities. Because frequency is equal to omega over 2 pi and time period is 2 pi over omega, and zeta is equal to coefficients of the critical damping. So in this way you can compute and interrelate all these three quantities. Now the velocity as a function of the time period, displacement was this one, and when we multiplied the displacement with omega n, we obtained this value. Again this was 5, but this was slightly increased. This was 7, although it is increasing, but here it is decreasing. So this is the velocity response for the same displacement response. the velocity response is obtained. Now the displacement and acceleration response. The relationships are written here. This pseudo इनको हम कहते हैं because ये एक fixed value पे है. Pseudo velocity response, pseudo acceleration response from the displacement response. So we have the displacement. We can obtain the acceleration. This one. When it is increasing, it decreases. It further increases, it decreases. So time period actually playing its role there. Overall, now convert all these parameters. Graph number 1, number 2, and number 3. 1 and 2, yes, 1 and 2. Displacement velocity, displacement acceleration. Now plotting all the three quantities, displacement, velocity, acceleration, as a function of time period on a single spectra is called as a DVA spectra. This is called as a DVA spectrum, and that is available for many different earthquake data that you are able to see for one specific time period. You can see simultaneously the acceleration, the velocity, and deformation at the same time. But how you can have to see it here, it is explained because the relation was already there and the three quantities was already computed in the previous slides. Let's say you are plotting now a single graph. You have the values of each one. Now when you plot it on a single graph, you try that the time period on x-axis is there, okay, for different time periods. Now the velocity will come. If you want to get the DVA spectra, the velocity comes on this axis, and then you have another line. This is the acceleration line, and this is the displacement acceleration. This is the velocity, and this is the time period. You can obtain a single curve. This is called as the DVA spectra. Now the point is how you can see all the quantities at one go. Let's say the time period 2 seconds, you want to see the three quantities. You will go first straight upward. For one zeta, one curve is there. This is for zeta 2%. Then you go upward and you have certain value. Let's say the displacement, you want to see the displacement, so you will draw the perpendicular on this line so that the 90 degree, and you can get the displacement. Similarly, against that line where it is crossing the vertical line, you go on the left hand side and draw the perpendicular and get the velocity value. And now where these two lines are crossing, you can now get the directions in this line on the acceleration, and then you are able to find out the acceleration value also. So one value, its arrows are shown here, that how you have to move. How you have to move, the arrows are shown here. This one, first go upward, then you get this value by taking the 90 degree. This line cross point is obtained, and on this curve. You touch the curve and get the value. Then you go to the left hand side and get the velocity, this arrow. On the same point you can go this side. You can get the acceleration. So all the three quantities can be obtained on the combined DVA spectrum. This is called as the DVA spectra, and a further explanation, you can plot it on a special graph that is available. DVA graph is available. Try to plot it, practice for it, and you can obtain the velocity, acceleration, and this is a further explanation of the DVA spectra. First you have a single value against the each case, and then you get the values for the different points. And the arrows that are shown, this is a one curve which is a response curve. You get the time period, go upside, touch the curve, then go take the perpendicular on deformation, take the perpendicular on the velocity, acceleration, and you can obtain the certain values. So in this way you are able to, from the DVA spectra, you are able to get all the three parameters. But this is for the one damping ratio, and you need the overall. If you see in the literature, lot of curves are available on one DVA spectra actually for the different damping ratios. So this curve you can see for the zero damping, for 2%, 5, 10%, 20% damping, 5 curves are available. And for the different values of the damping, you see that the damping is increasing, and accordingly the response is changing. And you can obtain from this graph now, if you want, let's say want to see for this case, you go upside and then take the perpendicular here and then take it here. So in this way you can take for the different time periods for any curve, you can determine the values of the. So this is basically the response spectra, real, based plotted on the real values, all the responses of the system, peak response you can see, and you can note down the value. Now the point is that how to use it and where to use it in structures. You have obtained the curve and you have now the response spectra. This is for the El Centro. This response spectra is for the El Centro. All these are the response spectra. You can see here. There are the different response spectra. This is for the El Centro for the different. You can see the response for the different damping ratio and the peak values of the ground acceleration, velocity, and the ground displacement. Response spectra for El Centro ground motion plotted with the normalized scale. This is with the normalized scale also now. I mean, you divide the acceleration by the certain the u g naught and the velocity. You multiplied with the standard g values. So normalized scale इसमें बता देते हैं. When you divide it with a certain value, u dot g d over u g naught, so then you can see the response. नॉर्मलाइज जब किया है तो आपने देख रहे हैं कि डॉटेड लाइंस आ गई हैं, स्ट्रेट लाइंस आर आल्सो obtained. In any problem, when you will solve the problem, so you can see the response spectrum. This is, let's say, for the 5% damping. इसको अगर आप आइडियलाइज करना है ना, तो ये फिर इसके वे है तो हाउ टू मेंशन डिटरमिन दीज पॉइंट्स, बिकॉज practically watching the response spectrum on irregular curve is little challenging. So इसको फिर idealize करते हैं where these points are obtained. I will tell you, these are called as the spectral region. acceleration sensitive है, ये जो region है first वाला ये acceleration sensitive है, फिर velocity sensitive है, ये displacement sensitive है. all the three spectral regions of the response spectra are very important, and you can obtain these values. ये जो values है ना, that how to obtain this alternative design spectra. We have to plot from the response spectra. We can obtain the design spectra. I will explain the steps also for how to plot the design spectra. So this is mainly the common response spectra which is widely used and available in the books also. The DVA spectra for the different damping ratios. And for any values, how to see the different deformation and acceleration response, you can also see that. And based on that, there is an example. So after a break, we start with the example of the problem. Short break.